Hello and welcome back to another episode of Mr. Walker's Chemistry. Today we're going to be covering orbital diagrams, and this goes along with our electron unit that we've been in. Okay, so the objective. By the end of this video you should be able to draw an electron orbital diagram. So what is an electron orbital diagram? Well, here are 4 examples. Okay, so let me explain what this is. Hopefully, if you've watched the previous videos, the 1s2, 2s2, 2p3, 2 etc., that looks very familiar to you, and that represents an electron configuration. So what an orbital diagram is that we're applying arrows essentially to represent electrons to our electron configurations that we already have. So for example, if we look at 1s2, which would be helium, okay, it has 2 electrons, one spinning up and one spinning down. Okay, so electrons have opposite spins. We covered that in one of the early lectures about electrons. So these arrows represent the spin, and you can see they always go in opposite directions. Okay, you cannot have 2 in the same orbital that spin the same way. So then these boxes represent the orbital. Alright, so you've got an electron configuration, you have a box to represent the orbital, and arrows to represent electrons. So when we get down to these here, okay, 1s2, okay, so we've got our box to represent the s orbital, then we've got 2 arrows, one up, one down to represent the 2 electrons. Same thing for 2s, so we've got another box to represent the 2s, and then one up, one down to represent the 2 electrons. And finally, we have 3 boxes because p orbitals can have 3 separate orbitals. Remember, they've got the one in the x direction, one in the y direction, and one in the z direction. So now we have, think of this as 2px, 2py, 2pz, and then you can only have 1 electron spinning in each way. Okay. And then we're going to learn about a rule today called Hund's rule. Hund's rule says you must fill each orbital with at least 1 electron before you move on to the next one. Okay, so we're going to do 3 up arrows before we start going back and doing down arrows. We're going to do lots of practice with these. Okay, so as I've already mentioned, you've already learned how to do electron configurations. Now we're going to learn how to write them out in diagrams. Okay, so just a quick review. Do this. What's the electron configuration for xenon, Xe? If you can't do this, if you can't answer this, alright, go back, relearn that. Because if you can't do an electron configuration, these orbitals become a lot trickier. Okay? So go back, do these, pause, try it out. Alright, so converting an electron configuration into an orbital diagram. If I'm given this, 1s2, 2s2, 2p3, let's write it out. So the first thing I want to do is the 1s2, 2s2, 2p3, okay? And I put some space in between here. And I did that because I want to have room to write my boxes or lines, whichever you prefer. For this, I'll do it both ways. So we're going to do, okay, we'll do this one more time. And I'm going to show you two ways that you might see this. You might see the boxes like you had in the previous slide here. Okay. So for the s's, we only need 1 box each because there can only be 1 s orbital. But for p, we're going to need 3 boxes. Okay. If I were a perfect artist, I'd put them together, but I'm not, obviously. So there we go. So now we've got our x, y, and z orbitals here. Okay, x, y, and z. You can also do lines, and you would just do these just like you do the boxes, except that you just don't do a box, you just do a line. Okay, so 1 line for the s's and 3 lines for the p's. Alright, so now we need to apply some rules. We've got Pauli exclusion principle, which says we can't have more than 2 in any orbital, and that they must go in opposite directions. They must spin in opposite directions. And then we've got this new thing, Hund's rule, which says you have to fill each orbital before you move on to the next one with at least one electron. Okay, so the first thing, we're going to fill our lowest level here. So we're going to have one going up and one going down. That's our 2. Same thing for this one, because we have 2 electrons. Alright, so on your lines it would look the same. You're just doing up and down arrows on the lines instead. And now we get to the P. Well, the P is tricky because we've got 3. Alright, so we filled all our lower orbitals, so we're good. Now we need to go back and fill these. Well, we need to put at least 1 in each, so I'm just going to do 3 up arrows here. You could also do 3 down arrows, so I'll just show that here. So we'll do 3 down arrows here. Doesn't matter which one you do, they just all have to be the same. Okay? So now we've got 3. Well, is 3 all we needed? Yes. So are we done? Yes. Okay? This satisfies this electron configuration. We're going to do some more. And these can get really far out there, these orbital diagrams. I mean, you start getting to things in the d orbitals and you could have some pretty crazy stuff. Alright, so let's write out orbital diagrams for oxygen, neon. I'm going to let you guys are going to do hydrogen and phosphorus. Okay, so I'll do these 2, you guys do hydrogen and phosphorus when I finish. You can pause the video and try them on your own. So oxygen, alright, be sure to pull up a periodic table, find oxygen. You'll find that oxygen is in the 2p block and it is the 4th one over. So we're going to do 1s2 to fill in hydrogen and helium, 2s2 to fill in lithium and beryllium, and now 2p4 to get to oxygen. This is my electron configuration. Now let's convert it into an orbital diagram. So 1 line for the s, for each of the s's, and then 3 lines for the p. Okay. It's customary to write which orbital the line represents underneath. That's why you've seen it in all of those others. Okay. I'm going to write this one a little bit differently. This might help some of you. So I'm going to write that as 2px, 2py, and 2pz. This helps some people because now you can see where the 3 different orbitals come from, why you've got 3 lines, and all of these are typically just written as 2p. Okay, and we've got 4. Alright, so let's fill them in. 1 up, 1 down. 1 up, 1 down, because we've got 2. Okay, now we get 4. First thing, 1 in each. Okay. 1 in each, and then we need to go back. Well, we've only got 3, so let's do a 4th. So I'm just going to go back to my first one here and do a down arrow. So now I've got 1, 2, 3, 4. Okay, and now we're all done. Okay, simple enough. So that one was oxygen. Alright, so I'm going to erase that, and then I'm going to do neon. So now neon is in the 2p block, and it's at the very end. It's what we call a noble gas. Alright, so 1s2, 2s2, 2p, and it is the 6th one in that block, so it's 2p6. So we just write these out. 1, 2, 3. Alright. Remember, this is the x, the y, and the z. Alright. So 1 down, 1 up, 1 down, 1 up to represent the 2 there. Now we've got 6. So 1 up, 1 up, 1 up, 1, 2, 3, 4, 5, 6. All done. So this one would be neon. Now I'm gonna jump down. I'm gonna do one that I actually didn't list here, just so you can see what a d orbital might look like. So let me try and think of one that could be there. Cobalt, I'm pretty sure is the 3rd one over. Let me pull up a periodic table here, and so I know where it is. So periodic table, here we go. Okay, oh nope, cobalt's all the way over here. So we're going to do titanium. It's the second one in the D block. So we'll do titanium here. Makes it a little easier. So let's do that. So we're going to do titanium. Alright, so titanium is the second one in 3D block. So if you go back to the other one, see the overlay, you'll see that I'm in the 3D block there. So we've got to get all the way down there. So we've got to do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. So you can see that these things get very long if you go way down the periodic table. In class I'll teach you guys a shorthand way to save you some time. Alright, also in class I'll discuss why we go from 4s to 3d. Why doesn't it keep going up in energy level? Alright, so here we go. So 1s2, 2s2, 3 for 2p6, 3s2, 2, 3, 4, 3p6, 1 for 4s2, and now we're at a D. How many orbitals can a D have? D, remember, can have 5, so we need to draw 5 lines. 1, 2, 3, 4, and 5, and this is my 3D2. Alright, so here we go. Up arrow, down arrow, 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 up arrow, up arrow, up arrow, down arrow, down arrow, down arrow. Okay, there we go. So now we're at 6. Then we have 2. Alright, so now we've only got 2. So we're just going to go 1 up, 1 up. And there I've reached the end. That's 2. Completely done. Yes, I have some empty orbitals. That's okay. Remember, you can have 0, 1, or 2 in an orbital, but no more. Alright, so there's titanium. That's one that's further down. Mainly I did this so that you could see what a D would look like, because remember, you've got 5 orbitals to do, and how you might get there as a quick refresher on electron configurations. You got to go to the end of a block, 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 okay? Each of these represents the end of a block, so then you go to the next one, and that's where we get to our final one. So, do pause here, do hydrogen, do phosphorus. They're not too hard. They're good starter ones to see if you're getting it. Alright, bring in your practice to class and be sure to ask questions. So for review, according to Hund's rule, that an orbital can take on 1 electron unless it's forced to take 2, so that's why when we go back to things like 2p3, we do 3 up arrows and no down arrows. According to the Pauli exclusion principle, an orbital can only take 2 electrons maximum, 1 going up and 1 going down, thus the up and down arrows. And just be able to write out the electron configuration and then draw lines or boxes that correspond with those, and then fill in the electrons as needed. Okay? Alright, so that's it for today. Hope you learned something, and I'll see you next time.